For this last section, I want to give a summary of the different techniques that we've encountered when it comes to partial fraction expansions. So there are two main cases to keep in mind. So here we want to know the partial fraction expansion of p polynomial divided by q. In the first case, we have that the degree of p of x is bigger than or equal to the degree of q of x, the denominator, and in that case you have to do a Euclidean division. And Euclidean division then gives you that p divided by q is equal to another polynomial, let's call it s, plus a remainder divided by q of x. And here we know that the degree of the remainder is less than or equal to, or sorry, strictly less than the degree of q of x. And once you've done the expansion or the division, then you can focus on the remainder divided by the quotient instead. So then for the second case, here we assume that degree p is less than degree q, possibly after Euclidean division as on the left. And then there are three different scenarios that can happen. Either they happen separately or they happen together. So we've covered the case where q has some unique roots. Alpha 1, alpha 2, up to alpha m, let's say. And then the partial fraction expansion gives you coefficient a1x minus alpha 1 plus a2x minus alpha 2 plus and so on plus am x minus alpha m. And then the second case that can happen either separately again or in conjunction with the first is that qx has an irreducible quadratic factor so let's say something of the form x squared plus ex plus f. Then what does that do to our partial fraction expansion? Well, then p over q has whatever the other roots contribute, but plus something with the quadratic factor in the denominator, dot dot dot, and a linear polynomial in the numerator. So the denominator here is that irreducible quadratic factor. And then see what happens if we have roots with multiplicity higher than 1. So let's say the multiplicity here is m, then our partial fraction expansion becomes p of x, q of x is equal to what you get from the other roots or quadratic factors, and then for the root with multiplicity m, you get a1x minus alpha plus a2x minus alpha squared plus dot 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 amx minus alpha to the power m. And throughout all of this, you have to keep in mind that A, B, and C can happen concurrently at the same time. So you could have a Q of x that has some unique roots, some quadratic factors that are not reducible, and some roots with higher multiplicity. And what you do in that case is you just add the terms that you need for the different partial fraction extensions.